So good morning everyone. So yesterday we have discussed about the chemical properties of the carboxylic acid, few of chemical properties of the carboxylic acid. If you recall the chemical properties of carboxylic acid due to the cleavage of so due to the cleavage of OH bond and due to the cleavage of COH bond, and next these are known as nucleophilic substitution reactions, and next decarboxylation. So that means removal of carbon dioxide, and then substitution reaction on alkyl part of carboxylic acid. So we are going to learn in our syllabus we have these four type of reaction. So yesterday we have completed first one, that is the reactions due to the cleavage of OH1. So this reaction reflects the acidic nature of carboxylic acid. So generally the metals and bases will give this reaction. And next, in the cleavage of OH bond, and that is also known as nucleophilic substitution reactions. Under nucleophilic substitution reactions, we have studied about the preparation of acid derivatives. First one is ester, second one is acyl halide, and third one is amide. Fourth one is acetic anhydride. So yesterday we have seen about the mechanism of the preparation of all these four acid derivatives. And next one is similar to that one, that is reduction reactions. So the reduction of carboxylic acids using the catalyst or reagents, generally we are using for that purpose lithium aluminum hydride, sodium borohydride, and boron trihydrate or BH3, or sometimes the dimer of that one, that is B2H6 diborane, also we use for the reduction of carboxylic acid. The reduction of carboxylic acid results, so ultimate product is alcohol, but directly we do not get alcohol. So first what happens, this carboxylic acid, first on reduction, so generally we denote reduction just placing a hydrogen on aroma, okay, both the aroma. So first what we get the corresponding carbonyl compounds, that is aldehyde. Again, on further reduction of aldehyde, so lastly we get alcohol as our end product or final product. So that means it is a two-step reaction. So first what happens, the conversion of carboxylic acid. So first what happens, this carboxylic acid converted to the corresponding carbonyl compound, and this carbonyl compound again undergo the reduction reaction to give our end product, that is alcohol. So this is the way of reduction of carboxylic acid. And for this purpose we are using namely two reagents. What are those? So particularly we are using some reagents like lithium aluminum hydride and sodium borohydride. So lithium aluminum hydride and sodium borohydride both will acts as a donors of H minus, that is also known as a hydride ion. And the second last one is BH3, BH3, that is boron. So boron, it is actually it is a what we say, electron deficient species. Why? Because it has one vacant orbital. Okay, so later we will in our syllabus we have only the mechanism of lithium reduction of carboxylic acid with lithium aluminum hydride. Okay, so let's see the mechanism. So how we can get all those things. So in our so right now you can just visualize only these things. In first step, what happens? This acid, whenever it is treated with the lithium aluminum hydride, we got what? A salt. Okay, so that accompanies releasing of hydrogen gas. So let's see how it happens or how it takes place. So what is the character of acid? So the character of acid is releasing of H plus ion. So when it is releases H plus ion, it gives a carboxylate ion. Next, this H plus ion readily reacts with aluminum hydride. So this is lithium aluminum hydride structure. Aluminum and boron both belongs to third group. So this is the lithium aluminum hydride. So that's why aluminum acquires a negative charge, and that's why it acts as a source of H minus hydride ion. So this part will be eliminated as H minus. This H minus will take up this H plus to form Rimshu, Rimshu. Yeah, chatting हो रही थी हो रही so that results what releasing of carbon dioxide sorry hydrogen gas. So this is the first step. So in that first step what we got this will be converted as so I will show you. So it will be converted as carboxylate ion CO minus and this lithium. This is salt, lithium salt of carboxylate ion, along with we get AlH3. Okay, so this is the first step. Okay, sometimes here see what happens. This lithium aluminum hydride has one vacant orbital, so that's why it can act as a electrophile. So due to this, what happens? It this negative charge, or you can say the lone pair of electrons are donated to this. Thereby, we can expect this structure C double bond O Al H3. So now what happens? It will get acquire negative charge, and it will be lithium plus ion will be associated to negative charge. So both are same. So here he directly shown this one. So this is the first step. What is liberation of hydrogen gas? And next step what happens? So next step this carboxylate ion again reacts with one more molecule or one more molecule of lithium aluminum hydride. Lithium aluminum hydride. So thereby we get carbonyl compound. So let's see how. So this is carboxylate ion, and when it reacts with lithium aluminum sorry, so this is actually I supposed to write this one as aluminum. So this is H, this is H, 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 and it occurs negative charge, and here positive charge. Here what happens? So the lone pair of electrons of the double bonded, it will attack on aluminum. At the same time, what happens? The H minus will be attacked on carbonyl carbon. So thereby what we get? So R and here O double bond, and it already form a bond with aluminum. So that's why it acquire positive charge, and this is H, and this is H. Okay, so it is minus and here plus. And here we have O minus and this one is H plus. Sorry. Okay, so already it is attacked on the carbonyl carbon. So that's why what happens is the double bond is completely shifted on oxygen. And now see this lithium. Okay, so here I need to do. Okay, yes. Now here we have one hydrogen, and now the lithium will comes here. Next step, what happens? This double bond completely shifted here, so thereby it will be shifted like this. So again what happens? So this will be converted as this part is converted as aldehydic part, and this will be converted as O minus, and this is lithium plus, and here this aluminum H like this, two hydrogens. Okay, not sorry, we have one more hydrogen. Okay, already that is used in the liberation of this one. Okay, and so this is what first step, that is first step is what the removal of hydrogen gas. The second step is what the formation of carbonyl compound. Again, this carbonyl compound has the tendency to participate in the reduction reaction, so it readily reacts with one more lithium aluminum hydride. So how it happens I will show you. Okay, need not to bother about byproducts. So we need to concentrate upon the main product. Okay, so here, so this is aldehyde, and again, this aldehydic part will react with the lithium aluminum hydride. So lithium aluminum hydride acts as a source of hydride ion. So it attacks here, then double bond shifted here. So thereby what happens? So RCH, and this is H. Now this oxygen will get the negative charge. At the same time, aluminum, it may be lithium aluminum hydride may converted as AlH3. So this negative charge attacks here. So again, thereby what happens? This is CH2 and O minus, so oxygen will form a bond with this. So this one, and it gets negative charge, and here this is positive. So by means of this, the remaining these three hydrogens will be replaced by these aldehydes in similar manner. So here three more aldehydic molecule. So same thing. See here, see, if you want to, okay, if you want to check it, I will show you how it happens. So here hydrogen, this is hydrogen, this is hydrogen, and it acts as a source of H minus ion. So this H minus ion attacks here. So thereby again it attacks here. So then what happened? So this side RCH2O minus, again lithium. Here one H, here another H. Here what happens? This hydrogen is replaced with oxygen, carbonyl oxygen, and this is H, this is H, this is H. So this is R. So by this manner, what happened? These two remaining hydrogens also be replaced with this RCH2O bond. So thereby what we get? We get this one. RCH2O taken 4 times, Al minus Li plus 3. So then acidic hydrolysis will give our, so after hydrolysis of this one, so once the two hydrogens are replaced with these two hydrogen, once these two hydrogens are replaced with uh, so here I'm showing same manner O CH2 R, here also O CH2 R. So it will acquire negative charge and the lithium ion here. So this, when this is treated with acidic hydrolysis, then what happens? So this part, so this part will taken up or accept one hydrogen ion or H plus ion. So then it may be converted as OH. So 4 moles of OH. So this product we get this product. Okay, so this is the reduction of carboxylic acids. Okay, so first part is liberation of hydrogen gas, second one is formation of carbonyl compound, and third one is formation of the substitution or replacement of all 4 hydrogens with RCH2O minus, or in short you can say alkoxides, followed by acidic hydrolysis will give our final end product, that is CH2OH or CH2OH, that is alkoxide. The similar reaction or similar mechanism we can expect with sodium borohydride also. Okay, so when this is BH3 is treated, so also here also similar product we may get, but BH3 has more reactivity compared to lithium aluminum hydride. It can has the capability to reduce double bond also, but here see, in one example here, this reagent doesn't affect the double bond. So that means we can use for selective reductions. So it is selectively reduce only carbonyl function group. It doesn't reduce the double bond. Whereas if you run, if you carried out the same reaction with BH3, then what happens? This carboxylic group will be reduced to corresponding alkyl, as well as this double bond also reduced to this alkane also reduced to alkane. So BH3 is not selective reducing agent. Yeah? It has so that's why for selective reducing reagent, selective reductions, we have the space, we have the provision to select a suitable reagent. So here, if you want to reduce only carbonyl compound or carboxylic function group, or else carbonyl compound, then we can go, or we can go with the lithium aluminum hydride, or else sodium borohydride. But if you want to reduce both, then these are not sufficient. These are not capable enough. So at that time, we need to change, or we need to go for another. That is what BH3. So BH3 has the tendency to reduce COOH group as well as this alkene part. Okay. So this is about the reduction of carboxylic acid. And next one, decarboxylation reactions. So what is decarboxylation? Removal of carbon dioxide from carboxylic acid. So when we remove CO2 group from carboxylic acid, we get what? Corresponding alkane. So it is general reaction in during the course of reactions, or somewhere, for example, in synthesis of monocarboxylic acid via ethyl acetate. So generally what we do, so when we have this one, this is what dicarboxylic acid. So here, when upon the heating or with soda lime is nothing but NaOH with, and CaO, calcium oxide. This is known as soda lime. In simply on heating also what happens, this carbon dioxide will be removed, and then we end up with a monocarboxylic acid. So this reaction here, see, this carbon dioxide is removed, this hydrogen now is directly attached to this carbon. Okay, so this can be done generally in last year in intermediate also we have studied decarboxylation reaction with soda lime or in simple heating. But we have some applications. If we change the conditions or reagent, we may get different products. Okay, so here in the under this topic we are going to study some Neumund reactions. Those are very important. So first one is Huns-Dekker reaction. So already you have studied in intermediate second year also. So in this Huns-Dekker reaction, we prepare what? We convert carboxylic acids into the alkyl halides. Okay, how? Let's see. So Huns-Dekker reaction, generally what we do, we take first we take carboxylic acid, and this carboxylic acid, it is treated with silver salt. Then we get silver carboxylate, it is a salt. So this is our starting material. So silver carboxylate. When this silver carboxylate treated with bromine, so again here in presence of phosphorus, so generally we execute this reaction in presence of phosphorus, so that phosphorus acts as a catalyzing agent. So but here we are running, he used CCl4, that is non-polar medium, and try CCl4 at 76 degrees centigrade. What we get? We get alkyl halide along with releasing of carbon dioxide. So along releasing of carbon dioxide, and we have one more byproduct, that is silver bromide, that is a yellow colored precipitate. And this reaction is proceed through via formation of free radical. So free radical type of mechanism we can expect here. So let's see how it was. So see, so when this silver salt of carboxylate is reacted with bromine, so what happens? I will show you. Okay, so this is silver salt of carboxylate. So it will get negative charge, and it will have positive charge. And this is bromine. Halogens are also known as neutral electrophiles. So what happens? So initially this negative charge attacks on one of the bromine atoms. So thereby it will be removed as Br minus, and from here Ag plus. So Ag plus and Br minus both will remove as AgBr. So this is AgBr. And so sorry, it is bromide. So this product we made it. Next up, what happens immediately? It is both are oxygen and bromine, both are higher electronegative in nature. So that's why they cannot exist. They cannot bind through a covalent bond. So what happens? This bond immediately undergo homolytic cleavage. Homolytic cleavage means what? So equal sharing of bond pair of elements. That results the formation of this one, a free radical. So this is bromine atom. So this is free radical. Again, what happens? It will be this bond again undergo homolytic cleavage. So then we get what? R free radical, and this is C double bond O, and here it have one electron, and that is connected to the oxygen. This single electron and this single, those are unhybridized electron. Again undergo lateral overlapping and form pi bond. So that is carbon dioxide. And again in the reaction mixture we have one more species, that is Br minus, Br free radical. Now this Br free radical and alkyl free radical both will combine to form our desired product. What is that? Alkyl bromide. So this is the way of mechanism how the salt of silver, salt of carboxylate is converted into corresponding bromide. Okay, so this is which reaction? Huns-Dekker. So this one is invented or proposed by Huns-Dekker. So that's why this name is this reaction named after Huns-Dekker. Okay, so in this reaction, what we have done? We have removed the carbon dioxide. Okay, so these are the some examples. Next, another reaction is very important reaction, that is Same, this is same reaction and one Schmidt reaction. So it is very important. So Schmidt reaction. So if you learn about Schmidt, then we can. It is become very easy to learn another reaction, that is the Arndt-Esther reaction. That is also very similar. This Arndt-Esther reaction is also known as homologous series homologous of carboxylic acid. Okay. Okay, so come to Schmidt reaction. In the Schmidt reaction, our starting material is carboxylic acid. When this carboxylic acid is treated with hydrozoic acid, so here see hydrozoic acid means N3H. N3H already we have studied in our intermediate N3H, and that is hydrozoic acid. Hydrozoic acid. So it is hydrozoic acid. So this whenever this hydrozoic acid, that is N3H, is treated with carboxylic acid, so then what happens? The removal of water molecule takes place. This H and this OH will be removed, and thereby we get this as a N3. Directly we can write N3, but it is difficult to understand during the mechanism. So this is N. This is N double bond N double bond N. It will get negative charge and it will get positive charge. So this is okay. So we may get this product. So this is known as what we say. It is known as okay. This one we get this one. Okay, this is a resonating structure. We can write the resonance also. This is known as SLM and hydrozoic acid, and this it is also known as carbamate also. This is also known as carbamate, and not carbamate. It is an unstable product, and generally we say acid azide. We say this one as acid azide. Acid azide, not acid azide. Acid azide. Okay, see, let's see the resonance of this azide, this part. So it can be written as n minus the single. Okay, and so I will show you the resonance of this one. Okay. If you write the resonance, how it happens, how it seems like this. So when this double bond is shifted here, then what happens? R C double bond O, this nitrogen will get the what positive charge, and this will get neutralized, and this is negative charge. When again this bond comes here and this electrons comes here, so again then we get R C double bond O, N double bond N double bond N, and this is plus, and here we may have lone pair of electrons. Okay, so need not to bother about this. So here we have the mechanism, and see, so first step is formation. This is acid, so what is the role of acid? Acid donates the H plus ion, so that H. So here see, you may ask that okay, this is carboxylic acid, and here why we are maintaining this acidic medium means this is the inorganic acid. Inorganic acids are more acidic than carboxylic acid, so this will donate the electron, so it will accept. Again, if this negative charge attacks here, then we may get acid as well. Okay. So the first step is that the formation of removal of water, and that results the formation of this one, this compound, this one. Now this one is undergo the rearrangement. So I am writing here. Okay. So first the first initial rastana I am writing from first onwards. This is HN3 in presence of acid. So here what happens? Removal of water takes place. So thereby we get R C double bond N double bond N double bond N minus N plus. And next step is what? This may undergo rearrangement. So our resonance. So then what happens? This bond shifts here. So there we may get C double bond O N minus and the double bond becomes a single bond, and the positive charge again also retains. Why? Because nitrogen has 4 bonds. Actually nitrogen should have 3 bonds. Again if shifts here, again what happens, this double bond shifts here. Okay, again we may get initial starting one. So this is the resonance. So whatever product or intermediate product we have obtained, that will be stabilized by the resonance. In next step what happens, see, next step what happens, this C double bond O, and this is N, uh, and it may undergo rearrangement reaction. So how it happens, let's see. So this is N minus, so this is N plus triple bond. Now what happens, this bond is shifted here, so that facilitates the removal of nitrogen gas. So thereby we will get RC double bond O N minus, and it lost 1 electron. So that's why here I am showing a vacant orbital. So this is known as electrophile, electron deficient species. Electron deficient species. Now this electron deficient species undergo rearrangement. So how it rearrangements, this bond shifts here, then this bond shifted here. So this is known as rearrangement reaction. So rearrangement, rearrangement. So then what happens, this R will attach to the nitrogen. So now this single bond becomes as a double bond, and this is, so this is known as ketene. This is known as ketene. Sorry, not ketene, isocyanate. So this is known as isocyanate. This is known as isocyanate, and this is ketene. This part is known as ketene. So this part is known as ketene. So this is ketene. Ketene. This is isocyanate. Isocyanate. This part is isocyanate. So here see how it happens like this. Here see. So this is the first formation of this one, hydrozoic part. After removal of water, we got what we got, this one. So this is the resonance structure. This will be resonating, and this is rearrangement after removal of nitrogen. What happens? Rearrangement taken place, and due to rearrangement, we got an intermediate that is known as isocyanate. And next, hydrolysis. Hydrolysis of isocyanate. What happens? Okay. Hydrolysis means it is reacts with water. So here see, this is the water molecule. So this always the water attacks on this carbonyl carbon. This bond shifts here. So thereby what we get, R N. This is negative charge, and C double bond O, and this is O H H. So this will get the positive charge, and here what happens? The proton will be eliminated. This proton attached to this nitrogen bond, and then we get R N H, C double bond O, and OH. And next step is decarboxylation. So shifting of this bond. So when this bond shifted here, then what happens? It will be shifted here. So then what we get? So this part will be removed as carbon dioxide. So then RNH, that nitrogen will get negative charge. Along with what happens? We got H plus, H plus, and which gas is removing? Plus here I am writing here CO2 minus, CO2 carbon dioxide. Next, this H minus attacks on this RNH minus, so thereby we get the amines RNH2. So this is the mechanism. So here you can see the same thing. So that means whenever carboxylic acid is treated with acid, hydrozoic acid followed by hydrolysis, we get one amines. In Hansa-Decker, what we got? We got alkyl halides. And next, by Schmidt reaction, what we are getting? We are obtaining amines, primary amines. Also, we can also get secondary amines also, no problem. Okay. So this is another example, the mechanism. This is again this reaction. If this reaction is carried out, here this is another reaction. It is a replica, or we can say extension, or somewhat modification to a previous one. This is Arndt-Ester reaction. In that Arndt-Ester reaction, we are starting with acid halide. So that means first we react, we take carboxylic acid, and this carboxylic acid will react with thionyl chloride. So we get acid halide. And next, this acyl halide is allowed to react with this one, methyl here see. The name of this compound is diazomethane. CH2N2 is also known as diazomethane. So when it is treated with acid halide, it is allowed to react with diazomethane. What happens? Removal of H plus takes place here. This Cl and one of hydrogen will be eliminated. So thereby we get RCH2 here CH, and then here we get same thing. Okay, and this part will get the negative charge. This will get the negative charge. It has negative charge. Okay, I will show you how diazomethane. Okay, if you see the structure of diazomethane, you can understand. So first step is what? Conversion of carboxylic acid into the corresponding acyl halide. The next diazomethane. So diazomethane. So let's see structure or resonance. Okay, CH2, CH2 double bond N, double bond N. So this is positive charge. So this is lone pair of electron. Sorry, it is negative. So when it is shifts here, then what happens? It is bond shifted here. So again we may get like this CH2 minus, and here that double bond converted as single bond, and that double bond converted as triple bond, and already it is at positive charge. Again this steps here, and again it moves here. So again we get the similar previous one. So when this one is treated with acyl halide, so acyl halide means RC double bond O Cl plus. So I'm just elaborating the structure. C double bond N. So it will get positive charge. Double bond N minus. So removal of HCl. So thereby we get R C double bond O CH double bond N plus double bond N minus. Next step, what happens? This negative charge shifts here, then this bond shifted here. Again we will get a resonating structure. Then C double bond O. This CH becomes CH minus, that double bond becomes a single bond, and that double bond becomes a triple bond. It will acquire positive charge. Again this bond shifts here, so that accompanies what? That accompanies what? So I will write here. That gives, that liberates and removal of carbon nitrogen gas. So then we may get C double bond O CH minus. So CH minus, and by removal of this bond, this breaking hydrolytic cleavage of this bond, that accompanies creating vacant orbital. So this is known as ketene, and these ketenes again undergo rearrangement. So this bond shift, the negative charge shifts here, then this bond shifted here. So then what happens? This is known as rearrangement. So then what happens? R is attached to this CH. CH. Now this CH double bond C double bond. So this is known as ketene. And on hydrolysis, again what happens? So whenever it is treated with water, so the bond shifts here, attacks here, the bond shifts here. Okay, I will write continuation of this here. R CH minus. So that's in double bond becomes a single bond, and here OH H. So oxygen gets the positive charge. So deprotonation takes place as this proton will be shifted to directly I'm showing. This proton will be shifted to this proton will be shifted on or shifted to this one carbon ion. So thereby we get RCH2, then C double bond O H. So this is our final product. We started with this one again see. So how we got this one? We got this one by reacting. Sorry, how we got this one? Okay, so RC double bond OH, when that is treated with SOCl2 sulfonyl chloride we get. So our starting material is RCOH. Our end product is RCH10. Or in short, you can say our starting material has n number of carbon atoms and our end product will have n plus 1 number of carbon atoms. So that's why this anti-ester reaction is also known as homologous reaction or homogenation or homolog. So the homologous of carboxylic acid. So here see this reaction we can in short, in other words, we can say that we can start from less number of carbon atoms of carboxylic acid and end up with one more carbon number of carboxylic acid. So smaller or lower carboxylic acid to higher carboxylic acid. So this reaction generally used to prepare higher number of carbon atoms containing carboxylic acid with lower carboxylic acids. Okay, and then last one is HVZ reaction. So here a HVZ reaction involves the reaction of alpha hydrogens. HVZ reaction, this is proposed by Hall, Hollard, Zielinski. In short, this is also known as HVZ reaction. For this HVZ reaction, the condition is the carboxylic acid should have at least one of alpha hydrogen. So this is functional group adjacent to functional group carbon, that is known as alpha carbon. This alpha carbon, at least it should have one hydrogen, that the hydrogen is known as alpha hydrogen. So the carboxylic acid which has with at least one alpha hydrogen, so those will give uh, alpha halogenated carboxylic acids. So they may participate HVZ reaction. So here the reagent is, so here this reagent is generally you can show like this, or sometimes you can show Br2 plus PBr3. Why? Because this here this phosphorus is catalyst. This phosphorus reacts with bromine to give PBr3. Okay. So, some books he may mention as Br2 plus P or else Br2 plus PBr3. So both are same reagents. So both are same reagents and used for same purpose. That is what HVZ reaction. So here, see, look at the mechanism. Look at the mechanism. So this is here we have how many? Two alpha hydrogens. So that is alpha carbon, and we have how many? Two alpha hydrogens. So this here also we have two alpha hydrogens. So first step is what? And already I told you that the chlorination reaction we can use PCl3 or PCl5 or SOCl2. So these three reagents generally we use as chlorination. And here instead of chlorine, here we are using PBr3. So this PBr3 is used for bromination. So here what happens, this OH will be replaced by this bromine. So thereby we get this one. And next what happens here, this one of this hydrogen, alpha hydrogen bond shifts here, then this bond shifted here. So this is known as a tautomerization. In short, we can say tautomerization. So tautomerization. So this tautomerization will give enol. So this form is known as enol form. Enol form. Next, this in this enol form, what happens? This enol hydrogen will react with bromine. How? See, so this hydrogen, so I'm representing like this. This whenever this hydrogen is shifted here, then this bond. So then what happens? It accompanies the creating of negative charge. So this already I told you halogens are electron deficient species. It attacks here, so that facilitates the removal of H plus and Br minus HBr, and then we got what? Alpha halogenated, alpha bromination. Next, this species again reacts with another acid. So again, what happens? This part will be exchanged. Nucleophilic substitution taken place. So therefore, we get this product. This OH is substituted by Br. So then we get this one, and this will be converted as like this. So here, sir, what happened? This bromine part, alpha hydrogen is replaced with bromine. So this is known as alpha bromination, and this reaction is also known as HVZ reaction. Okay, so okay, this is the mechanism. If you want the detailed mechanism, you have the detailed mechanism. So this is about um, the reactions of decarboxylation as well as alpha hydrogen substitution reaction. So with this, we have completed the chemical properties of carboxylic acid. I hope you have understood this. Okay. So thank you.